Hey everyone, welcome back. I'm your math teacher, Mr. Boyden. Today we're getting into lesson 5 of integrals. We're going to be talking about the area between two curves and the average value of a function. These are basically two applications of integrals. So we've already learned how to do definite integrals. We already know about u substitution. Now we're going to start applying those and getting closer to solving some real questions. Okay, let's get after it. Okay, let's start with a question to get us thinking today. We want to find the area of the region that is between the functions f of x equals x and g of x equals x squared over the interval. Okay, so let's get started with a little bit of a picture. If we don't have a picture, I think it's going to be really difficult for us to understand what's going on. Today, if stuff doesn't make sense, maybe you want to pull up your phone, or if you have your computer, you want to get on Desmos, that's D-E-S-M-O-S, and actually graph some of the things we're looking at so you can see them. For some of these, I'm going to provide pictures. For some of them, I'm going to graph them by hand. I think it's important to understand how to do both, because you may or may not be able to use a calculator on your test, and if it's a non-calculator test, we don't want to get too reliant on technology. So it's helpful for learning to see it, but don't use it as a crutch. Okay, so for us, I'm going to start with my graph, and f of x equals x from 0 to 1 is what I'm told. Okay, now previously what we would have done is we'd say, oh, we'd shade this in, and you could integrate it if you wanted to with an integral, or if you wanted to, you could recognize that that's a triangle, and off you go, and you can find the area of a triangle. Today is a little different though, because we have two functions occurring simultaneously. So yes, we've got that, but we also have the function x squared. Okay. Now, don't want this to look like magic. Let me be transparent about how I'm doing this. This point right here is the point 1, 1. Okay? And I've done enough of these to understand that the intersection of these two functions is 1, 1. If you're not sure why, check this out. We could say, when we want to know when x squared is equal to x. Now, just by inspection, we can see there's only two ways that's going to happen. If you plug a 1 in here, 1 equals 1. Money. If you plug a 0 in here, 0 equals 0. Check it, there's the other intersection. Okay, so I can verify that way, or if we wanted, we could actually solve it out, but I think you can probably verify that one with inspection. Okay, so we have our points of intersection, and so what we want now, we want only the area between them. So we're not interested, and I'll shade it in a different color here, we are not interested in the area down below. And I'm shading that in blue. I hope that shows up for you. Okay, and so we just want the green. So what we're going to do is we're going to take the entire area, that entire triangle, and we're going to subtract off that blue region below. And when we do that, what will be left over is just the green. And so what that's going to look like is this. Integral, we were told to go from 0 to 1, so we can do that. We're going to take our top function minus our bottom function. And what that's going to look like in this particular example, 0 to 1, we have to ask which function was our greater function, our top function. Some students, when they learn this, get a little bit confused because they look at the equations and they say, oh, well, x squared appears to be greater than x does, so maybe x is the top function. That's not at all what that means. We have to look specifically over the interval we were given. We can do it visually on this one. The top function is the linear function, and the quadratic goes below. So what we're going to have is our top function x minus x squared dx. That's going to be the hardest part of today, is getting the setup. Once we have the setup, it's a total piece of cake. We're just going to integrate like we already know how. So let's do that. This is really good integral review for us. Okay, so this may be a point where you want to pause the video, try this one on your own to get your brain moving a little bit more. Okay, I'm going to try it. Okay, so x squared over 2 minus x cubed over 3 from 0 to 1. Let's plug those in. Plug in a 1, I get 1/2 minus 1/3. I'm not going to show the work on this next part. I can see that when I plug in a 0, that's all going to turn into 0, so that would just say minus 0 at the end. I'm not going to show the work on that though. And then I'm going to get a common denominator, so it's 3/6 minus 2/6. Sixths, that's a hard thing to say. 3/6 minus 2/6 is 1/6. And that is the area of that little region that's in between the curves. Okay, so there we go. A little bit more formally, this is the actual definition of it. This comes out of a textbook that I had from college. The area between two curves, if you have your functions f and g, and f is the top function. That's all that says. F is greater than or equal to g. We had that in our last example. Our linear function was greater over that interval. There's the interval. It's going to be like this. F of x minus g of x. I'm going to add one little annotation to that. I'm going to just call it top minus bottom. Okay, or the greater minus the lesser, something like that. That always helped me remember it and help me to understand it, and hopefully that helps you as well. Okay, we're going to go through a couple more examples and see a couple of the things that can come up in this topic. Okay, so again, very, very similar question. Maybe you want to try to pause this one and see if you can graph it on your own. Maybe check on Desmo, see how accurate your graph is. The graph doesn't have to be excellent. All the graph has to do is give us two things: the bounds and tell us which function is the greater function. If we have that information, then we're totally set and ready to go on this. So give this one a shot, unpause when you're ready. Okay. First thing I want to do is I want to graph it. First one's pretty easy to graph. It's an upward parabola with a vertex at the origin, so good enough. I also want to graph this one. I know it's a parabola because the negative, I know it opens downward. I need to figure out where the vertex is though, so I'm going to do that. So remember, the vertex is negative b over 2a, so negative b would be negative 2 over 2 times negative 1, and that would equal 1. I'm going to plug that back in and see what I get. I get 2 minus 1 equals 1. Okay. Looks like the vertex is at 1, 1. And it's some sort of a downward parabola. And I don't know where that intersection is, and I don't exactly know where that intersection is either. So what I'm going to do is I'm going to set these two parabolas equal to each other, and I'm going to try to figure out which one is the, or which, I know which one's the upper function. The upper one is this one that opens down. I'm trying to figure out where these points of intersection are. Okay, here's what that's going to look like. So I'm going to call that solving. Oops, I should spell solving correctly though. I'm going to call that solving for bounds. Okay, we're going to take x squared, we're going to set that equal to 2x minus x squared. And we're just going to use algebra steps. So it looks like I can move that x squared over, so 2x squared equals 2x, which means x squared equals x. I'm going to move the x to the other side, or we could remember this is the same exact thing we had before. There's only two values that can solve that. So we could say it's 0 and 0, or it's 1 and 1. So I'm going to put 0 or 1. Or we can solve it. So if we want to solve it, what we'll do is we'll rewrite that as x squared minus x equals 0. Then we can factor this. So we get x times x minus 1 equals 0. And then we can say, oh, that would create a 0, that would create a 1. So now we know those two pieces of information. So let's try to set up our integral now. We just called that solving for the bounds. So now I know the bounds go from 0 to 1. I need my top function and my bottom function. My top function, and folks, we're only looking in this interval right here. Because some people say, well, wait a minute. The upward parabola, x squared, goes way higher than the other parabola. And yes, it does. It goes up forever. But that's not what this is talking about. We're talking about only in our specific interval where we have that enclosed region, the region that's between the two functions. And that goes from here to here. And in that region, the top function is the downward facing parabola. So I'm going to grab that 2x minus x squared. And then the other function was x squared, so we're going to go minus x squared dx. Pretty easy to simplify that, so we're going to simplify before we integrate. So I get 2x minus 2x squared. Don't forget the dx. Okay, and let's keep going. Integrating, I get x cubed over 3 minus, or excuse me, that's a mistake. Let me go back to that. Okay, hold on a sec, we all make mistakes, right? Okay, so not x cubed, I added too much. Adding 1 to this makes it x squared. So I get 2x squared over 2 minus 2x cubed over 3. That's what I was thinking. And we still have our bounds. Notice right now that we can simplify this. 2 on top, 2 on bottom goes away. And so now we're going to plug in our bounds. And when I do that, I get 1 Plug in a 1. 1 cubed is 1. So 1 minus 2/3 minus, plug in a 0 into these, and they both 0 out. And so we get 1 minus 2/3, which is 1/3. Okay? These are a really standard testing type of question, and a question that's worth practicing. Let's do one that's a little bit more fun. Let's do the mustache problem. Okay, in the mustache problem, I'm calling it that because on the screen I've got two graphs, sine and cosine. And if you trace those, it kind of looks like a little mustache. Okay, and so I call it the mustache problem. And here's the question: the graphs of sine and cosine are going to intersect infinitely many times. Okay, it makes it a little funny to find the bounds if there's infinitely many intersections. Remember previously they had only 2 intersections, so we just found those 2 intersections and off we went. Those were the bounds. It's infinitely many here. We want to find the area of a region, only one, that is between the curves, bounded by consecutive intersections. Alright, so consecutive intersections means these things are going to keep intersecting forever. We want 2 that are in a row. So for example, and these are the ones I'm going to pick, I've got an intersection right here, I've got an intersection right there. They are in a row, they are consecutive. Okay, those are going to be my consecutive intersections. And so all we have to do, we're going to set up an integral. We know it's going to be sine and cosine. We just need to know what are the bounds, what's the upper function, and what's the lower function. If we know those things, then off we go. Okay, so what I'm going to look for first of all is just visually. Can I inspect this and see where the intersection is? It's not at 0, it's not at 1, it's somewhere in between 0 and 1. I think I'm going to have to use the unit circle to understand this actually. So unit circle, here we go. What we're looking for is a place where sine equals cosine. Or we're looking for a couple places, maybe even all the places. So right down here, no, that's not a match because that's 1, 0, so that's not a match. I go up to this first location, pi over 6, and we have root 3 over 2 and 1/2. Okay, so that's not a match. I go to the next place, root 2 over 2 and root 2 over 2. Okay, that's a match. That was pi over 4. Let's think about that. Pi divided by 4. Remembering that pi is 3.14 approximately. Divide that by 4, that's a little bit less than 1, right? Well, that's what our graph shows. This first intersection is at a place that's a little bit less than 1. So that gives me a lot of comfort in the fact that our lower bound is going to be pi over 4. Now don't get scared by that. It's no big deal that you can have pi over 4 in trigonometry and an integral. We already know how to do that, so it's not a big deal. Don't be intimidated by that. Let's find our next intersection. So what I want to do is I'm going to work my way around and find the next place that happens, where the x and the y value on the unit circle are equal. So is it here? Is it here? No. What about here? Ooh, negative root 2 over 2 and root 2 over 2. Close. No cigar, because one's negative, one's positive, so sorry about that. Keep going. Boop, 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 beep. Okay, there it is. It's going to be right there. And so I've got negative root 2 over 2 and root 2 over 2. Right? And that's at 5 pi over 4. Okay, let's think about that for a second. 5 over 4 is 1.25 multiplied by 3.14. That's going to be right in the neighborhood of 4. And I don't need to know exactly. I'm going to look at my picture. Right there, it's right in the neighborhood of 4. Okay, now if you're having trouble seeing mine, pull up Desmos. Just graph sine and cosine together. Find your little mustache. And there you go. I've got my bounds. Now the only thing left to do before we integrate is determine what's the upper function and what's the lower. So I'm looking here, my upper function is this one that I've drawn in purple, and that one, if I trace it back, it starts at the origin. So do you remember which one starts at the origin? Is it sine or is it cosine? Okay, because one of them starts up high, that's our lower function. One of them starts in the middle, that's our upper function over this interval. The one that starts here at 0, the one that has a 0 here, is the y value, which means that's sine. So we have sine of x. And then it must be minus cosine of x dx. Let's do just a little bit of integrating. And here we go. So sine integrates to negative cosine, minus cosine integrates to sine, and then we've got our bounds. 5 pi over 4 and pi over 4. Alright, let's plug them in and see what happens. So negative cosine of 5 pi over 4. And with these, I'm actually going to write all of them out because it's a little bit easier to make a mistake on this trig stuff than what we've done previously in the lesson. So I'm going to write out all the steps on this one. Minus sine, and it dawns on me that I forgot to write of x right there. Okay, sine of 5 pi over 4 minus forget your parentheses, because when you're subtracting, that can cause some problems. Negative cosine of pi over 4 minus sine of pi over 4. Okay? Now let's go through and get values for those. We'll simplify and we'll be done. So I'm going to actually pull up my unit circle again, and I'm going to redraw it down here, just because if I don't have that, I have the potential to get confused, and I think maybe you do too. So maybe it's worth, if you have it on your page, refer back to the unit circle you have on there. I don't have space right here, so I'm just going to redraw real quickly. And so I'm going to think about it like this. I only have 2 locations on the unit circle that I'm working on right now. I've got right here, and I've got right there. And for some reason, just having the visual in front of me, even if I don't label it, makes it way easier for me to think about this. Okay, so here I go. I'm going to do cosine of 5 pi over 4. 5 pi over 4 is down here. That would be, or to the left, so it's a negative. So negative root 2 over 2. And don't forget this negative right there. Let's go to the next chunk. Minus sine of 5 pi over 4. Down here, again, it's negative root 2 over 2. Okay, let's keep going. I get my big negative right there, parentheses, negative, cosine of pi over 4. Now we're up in quadrant 1, so it's positive. So root 2 over 2 minus sine of pi over 4. Again, that's positive, root 2 over 2. And now let's begin to simplify a little bit. Okay, so down here, I've got 2 negatives make a positive, so that's root 2 over 2. 2 negatives make a positive, so plus root 2 over 2. Minus a negative is plus root 2 over 2. And minus a negative is, hey, everything went positive, plus root 2 over 2. How many root 2's over 2 did I have? I have 1, 2, 3, 4 of them. So that's going to be 4 root 2 over 2, which is 2 root 2. That's it. Okay, so once we get our setup all done, these go pretty quickly and the process isn't too horrible. Be really careful. Make sure you are paying attention to detail here. If you don't include those parentheses, horrible things will happen to you. So be really, really careful, okay? That's a mistake a lot of people make. Alright, so now we've got another situation. In our first 2 examples, we had 2 points of intersection. In our third example, the mustache problem, we had 2 points of intersection. Now, we have 3 points of intersection. Now there's a little bit here that's really nice, because they told us the points of intersection, and negative 2, 10, and at least we can see that that's the origin. So we don't have to go find them, but we do have to be careful. And here's why. Remember how we said when we integrate, we want the top minus the bottom function? Take a look at this for a minute and see if you can figure out which function is the top function and which function is the bottom function. I don't think you're going to be able to do it. And I'm not taunting you either, because guys, no one can do it, okay? Look, this pink function right here, that one's on top, and then after that intersection, the pink one's on bottom. So this doesn't necessarily hold up. There's a really easy way to deal with this, though. We're just going to have to do 2 integrals. 2 integrals, twice as nice. Let's try it. Okay, so what I'm going to do is I'm going to have my first integral, and it's going to go from negative 2 to 0. And I'm going to take my top function, and I don't know if these are going to show clearly in the video or not, so I'll rewrite them. This one is 2x cubed minus x squared minus 5x. And this one is negative x squared plus 3x. Okay, so hopefully that's a little bit easier to see now. So we've got our top function and our bottom function. What is our top function? It's the pink one. The pink one is this 2x cubed minus x squared minus 5x. And then the bottom function is the blue one, the quadratic one. If you trace it, it just looks like a parabola. So then we have subtract parentheses the bottom function. Minus x squared plus 3x dx. And you know what? Don't get too comfortable because we're just getting started. Because we have these 2 different regions. So we take that, and I'm going to kind of box this off so it's not too much in the way. And we need to add to that another integral. Okay, now this one is going to go pick up right where we left off. We went negative 2 to 0. We're going to pick up at 0, and we're going to keep going until our other intersection at 2. Please notice when I say bounds, I'm picking x values. The way we would know that, here at the end it says dx, the bounds are typically x values, okay, because we're moving from left to right on this. Okay, so just look out for that, okay? So now I'm going to take, and my two functions have switched. Okay, so I need to represent that in my setup. So now the top function is the quadratic, so I get negative x squared plus 3x minus the other function, the cubic, 2x cubed minus x squared minus 5x dx. So now let's integrate it. We've got our setup all done. Let's try to figure out what our actual value is here. So to do so, we are going to do these totally independently, and so I'm going to start using a little bit more space here. I do want to combine them first, and so I'm still going to have my same integral from negative 2 to 0, and I'm going to look at these from highest degree to lowest. So I've got 2x cubed, nothing to combine with that, so 2x cubed. Okay, it looks like I have a minus x squared minus negative x squared. Interesting. So those two minuses are going to make a plus. With that minus, those are going to cancel out. That's a wonderful thing. That's going to save us some work. Good. So let's keep going then, and then I've got a minus 5x minus 3 more x, so it looks like I have minus 8x. Okay, that's good. Don't forget the dx. Let's go to the next one. Now I'm on to my second integral, from 0 to 2, and same thing. So I have a negative 2x cubed. I've got minus x squared minus negative x squared, so those cancel out again, and that's not surprising. I mean, if they canceled out subtracting one direction, they should cancel out the other way as well. So no surprise there. And then I've got 3x minus negative 5x, so that would be plus 8x dx. So I'm a little bit relieved. This just got a little bit easier when we simplified, because it was starting to look a little bit overwhelming up here. Okay, now let's go ahead and simplify this out. We'll actually do our integration. So that's going to turn into a 4, so we get 2x to the 4th over 4 minus 8x squared over 2. Don't forget your bounds, negative 2 to 0 plus. And now we have, so the x cubed is going to become x to the 4th, so we get negative 2x to the 4th over 4. And then we get plus 8x squared over 2. So the two sides look very, very similar. Again, not surprising, because all we have is a switching in signs with switching the order of multiplication up above. Okay, don't forget your bounds. 0, 2. And so now this should be fairly manageable. I am going to add in one little thing right here. I'm going to make these brackets just so it's really clear that we don't have a plus and a minus together. This vertical bar I'm putting in, you can turn that into a bracket at any time. Just make sure you bring its partner along to the dance. Okay, so we've got them there, and now I hope that's a little bit more clear. Let's start plugging in our numbers into the fundamental theorem and see what we get. And so I think I will color code the two sides just so we can see what came from where. So starting over here, I plug in a 0, and y'all, if you want to plug in the 0 and write all that out, you can. But that's an awful lot of symbols. And so what I'm thinking is when I plug in a 0 here, all that zeroes out. So I'm not going to write anything more than just 0. I am going to have to actually plug in the negative 2. And so I get minus, that's from the fundamental theorem, parentheses, and now we're going to plug in the negative 2. And I'm going to do a little bit of mental math here. And so what I'm seeing is when I plug in a negative 2 there to the 4th power, that would be 2, 4, 8, 16 to the 4th power. So I get 16, and 2/4 is 1/2. Half of 16 is 8. Let's plug in a negative 2 over here. Negative 2 squared is 4. And then 8 divided by 2 is also 4. So I get 4 times 4, so minus 16. Let's go to the other side. When I go to this one, plugging in a 2 will be worthwhile because those are actual numbers. And check it out. This is going to be basically the same stuff because we have very similar numbers. So plug in a 2, and 2, 4, 8, 16. 16 divided by 2 is 8. In this case, it's a negative 8 because there's a minus right there. And then plug in a 2 here, and I've got 2 times 2 is 4, so we get 4 times 8, 8 halves, which is 4, so that would be plus 16. When I plug in a 0, nothing happens, so minus 0. Now let's simplify. And so what do we have? We have 8 minus 16, so negative 8, but we're subtracting negative 8, so that's 8, plus negative 8 plus 16, so that's 8 again. 8 plus 8 equals 16. And we are all done. One of the ways this can get challenging is when we have a situation like this one. And notice, at certain parts of this, it's really difficult to tell what's the upper function and the lower function. Overall, it looks like the function in blue is above the function in red. When I draw straight down from the blue, I hit the red. However, there are a couple points on here. When I draw down from the blue, the thing that I hit is blue. And when I draw down from the red, the thing that I hit is red. So in those cases, it's not actually clear what the upper function and the lower function is. So what we have to do when that happens is, instead of integrating from left to right, we have to integrate from bottom to top. And so what I mean by that is, if you thought of this as being a 90-degree rotated situation, like from here I can say, well, the blue function is the right function, the blue function is still the right function, the blue function is still the right function, because the blue function is always the right function. And what I'm looking for is, every time I draw to the left from the blue function, I always hit the red, as opposed to when I draw downward from the blue function, sometimes I hit the blue function. So it works out a lot nicer if we do this horizontally. Now notice in the equations what's different to represent that fact. Instead of saying y equals on everything, these say x equals. Now it's going to work the exact same way. For some people it looks a little bit more confusing because, wait, but it's x equals and I don't understand that, that's not how we learned it. But that's okay. All the stuff we've learned is still going to apply here. We're going to have bounds, and we're going to have some greater function and some lesser function. Some we call it top and bottom, or right and left if you prefer in this case. And it's going to be the same stuff. So let's get to it. Remember, there's really only two things we have to do to get our setup. We have to find which function's the top function or the greater function, and we have to find our bounds. So let's get about doing that. So all I'm going to do to find the bounds is set these two functions equal. And so I get negative y squared plus 10 equals y minus 2 quantity squared. And now it's just algebra time. And so we're going to simplify these out. What I'm going to do over here is actually multiply those together. So I get negative y squared plus 10 equals y squared minus 4y plus, oops, not y, plus 4. Let me rewrite that so it's a little more clear. Plus 4. And let's continue. Okay, so I'm going to add this negative y over here, so I get 2y squared. And I'm going to subtract this 4 over there, so I get a 6. And I have a minus 4y. Dawns on me now that we should probably have this thing set equal to 0 since it's quadratic, so let's move the 6 over. And so I get 0 equals 2y squared minus 4y minus 6. Let's divide both sides by 2. Buy a little more space. And so now we've got y squared minus 2y minus 3. And let's see if we can factor that. So we get y and we get y. Let's get our parentheses. And I know it's going to have to be a 1 and a 3 because those are the only factors of 3. So I'm going to pop in a 1, I'm going to pop in a 3. I need to assign pluses and minuses to that so that they add together to be negative 2. So minus plus. So my y values are negative 1 or 3. Let's see if we can verify that visually based on the picture we had above. We had our graph up here, and we're claiming that it's when the y value is negative 1. Let's see, y value of negative 1 appears to be right here. Sure enough, that hits an intersection. Y value is 3. Sure enough, that hits an intersection as well. So visually, I can verify that that appears to be true. It gives me some confidence moving forward. That then allows me to start setting up my integral, which was from negative 1 to 3. And now all we have to do is figure out the greater function and the lesser function. Now, in the beginning of the lesson, I called it the top and the bottom, because when you're dealing with the y-axis, things are greater when they are above, when they're on top of the other. Now, if we were talking about the horizontal axis, the x-axis, which direction means greater? That one, okay, to the right. To the right means greater. So the function that is to the right is the function that's going to go first, or the function that has greater x values. And so taking a look with that in mind, the function that is further to the right is that blue function. That's the one that is negative y squared plus 10. That means our lesser function is this red function. We're going to subtract that off, and that was y minus 2 quantity squared. And the only big difference now is these were y values, and so we're going to write dy, signifying that, hey, our bounds, they're y values. They're not x values, they're y values. Okay, and so now we've got a setup. I'm going to box this off so it doesn't get confusing what's what. Okay, and now we're just integrating like we normally would. So let's go through that process. Here we go. I'm going to simplify first. So I get from negative 1 to 3, negative y squared plus 10 minus the whole shebang of that. Y squared minus 4y plus 2 quantity squared dy. I want to continue simplifying because I want my integration to be as simple as possible. So continue with the simplification. I get from negative 1 to 3, let's combine our like terms. Negative y minus y, or excuse me, negative y squared minus y squared, so negative 2y squared. I've got, let's see, I've got minus a negative 4y, so that's plus 4y. And then I have 10 minus, haha, I made a mistake. Did you catch it? Looks like it's right here. I think when you do negative 2 times negative 2, that's probably 4. So let me fix that real quick. So we had a y plus 4. So I have 10 minus 4, so that would be plus 6 dy. And so that just got a little bit easier. That's nice. Let's do this. So I get y cubed over 3. Don't forget that little negative 2 in front of it. And I've got y squared over 2. Don't forget the 4 in front of it. And I get a 6y. And we're going from 3 to negative 1. Or negative 1 to 3. Okay. I want to simplify this a little bit if I can. It looks like I can deal with the 4 and the 2 probably. So I think I'll take the time to do that right now, just to make this the smallest number of symbols in my final steps as possible. So negative 2y cubed over 3 plus 2y squared plus 6y. Okay, and now let's apply the fundamental theorem, and we're almost done. Here we go. So negative 1 to 3, I'm going to plug in the 3 first, and so I get negative 2 times 3 cubed over 3 plus 2 times 3 squared plus 6 times 3 minus all that same stuff, except we're going to plug in a negative 1. Okay, so negative 2 times negative 1 cubed over 3 plus 2 times negative 1 squared plus 6 times negative 1. And now we can simplify. Should be pretty easy. I think we're pretty well home free from here. So it looks like 3 squared is 27. 27 divided by 3 should be 9 times negative 2. This should be negative 18. Down here looks like 9 times 2, which would be positive 18. Ooh, that made it a little easier. And then we have 6 times 3. 6 times 3, interesting, is 18. Let's continue. Minus, alright, we got a negative in there. Don't worry, it's just a negative 1. It's not going to be hard. So negative 1 cubed is still negative 1 times negative. That gives us a positive 2/3. And it's going to be subtracted, but it is a positive 2/3. And let's go to the next one. Looks like 1 squared is, or negative 1 squared is 1 times 2 is just 2. And then we get minus 6. Now simplifying, negative 18 and 18 is easy to deal with. And down here 2 minus 6 is, we're going to rewrite that as 2/3 minus 4. So I get 18 minus 2/3 minus 4. Let's do things the easy way, not the hard way. And so 18 minus a negative 4, that would be 22 minus 2/3. Which would be the same as, let's get a common denominator, that would be 66 thirds minus 2/3 would be 64 thirds. And we're all set.